As if numbers weren't already complex and the work that we've been doing hasn't been complex, let's talk today about complex numbers. Now, what are these complex numbers and how do we begin to use them in our work with quadratics? So, complex numbers. Well, if you think of numbers as we've learned them up to now in algebra, we have real numbers. Remember the subsets of real numbers, and we had in early work we had a way to show the real number system, right? We had all real numbers, and we had the subsets, but they were all, everything kind of fit into that. Today we're going to talk about what's called an imaginary unit, and that imaginary unit is represented by the square root of a negative number. So if I have negative a, square root of negative a, well, when you think of square roots, you think of things like the square root of 4, right? We know that 2 times 2 is 4, so the square root of 4 is 2. But if I have a number in there that is a negative number, how am I going to get a square root? Well, we use the imaginary unit to show that. So the imaginary unit of negative a is I square root of a. So stick with me. Let's kind of look at the concept and then we'll back up into what we're doing here. So if I have the square root of negative 5, that is going to equal to I square root of 5. That's really kind of as far as you can take that. So it's not 5, it's not negative 1 times 5, it is I square root of 5. So if you have an imaginary number, if you have a square root, let's see how we write that as an imaginary unit. So we have the square root of negative 18. Well, I'm going to have that, because we're using imaginary units, so I'm going to have that as the square root of negative 1 times 18, right? Because I know the square root of negative 1 is going to be I. But what I can do then is separate that out. So that equals to the square root of negative 1 times the square root of 18. And then that equal I. Now the square root of 18 is the square root of 9 times the square root of 2, right? So that's I times 3 square root of 2. So then the way that I put that in order is simply equal 3I square root of 2. Now where are we going with all of this? So the imaginary number, this was the unit, right? So the imaginary number is any number in this form, a plus bi. Any number in this form where a and b, so a and b are real numbers. And b is not equal to 0, right? b is not going to be equal to 0. So imaginary numbers then, imaginary numbers and real numbers, they make up the set of what are called complex numbers. So you have imaginary numbers and real numbers together. So real numbers and imaginary numbers, they make up the set of what are called complex numbers. All right, so let's see how we can write complex numbers. So you can write a complex number in this form, a plus bi. And we said a and b are real numbers, right? And then that if b equals 0, the number a plus bi is going to be a real number, right? So this is a real number, this is a real number. But if b is equal to 0, we have a plus 0. Therefore, if b equals to 0, that's going to be a real number. If a equals 0 and b is not equal to 0, that number a plus bi is called a pure imaginary number. All right, so here's what this looks like. I'm going to draw it out for us in our little diagram here. So here we have the set of complex numbers. And we said they're in the form a plus bi. Now, what makes these up? So here we have real numbers, and we said real numbers can be a plus 0i, right? Over here we have imaginary numbers, where we have a plus bi, and b is not equal to 0. All right, so we have those there. And then inside that set, we have a subset called pure imaginary numbers, where we have 0 plus bi, and b is not equal to 0. All right, let's look at how we can use the complex numbers in a plane. So I'll get us a fresh plane over here. So we're already using the x-axis and the y-axis. But for our work here, what we can do is we can use that x-axis as is, and we can use that y-axis as the imaginary number. So we have, here we go, we got the x-axis, the y-axis, and we got the x-axis. So really in our work, we can make that y, so our y-axis is going to be our imaginary, just so we can kind of picture it. So that's our imaginary axis, and our x-axis, we'll call that the real axis. So x is going to be our real axis. All right, so we're going to look at the complex number plane. So in the complex number plane, if I have a point a comma b, for example, that's going to represent the complex number a plus bi. So to graph a complex number, we're going to locate the real part on the horizontal axis, right, and the imaginary part on the vertical axis. So let's do one. We're going to use the vertical axis and the horizontal axis. So if we have, for example, negative 5 plus 3i, and we want to graph that, and we want to know what the absolute value of each number is. So we want to know what the graph is and what the absolute value of each number is. So let's put that into absolute value. So we've got absolute value of negative 5 plus 3i. So that's going to equal the square root of negative 5 squared plus 3 squared. All right, so that's 25 plus 9, that's the square root of 34. So what do I do to graph it? So I got my absolute value of that first, so that's taken care of. So absolute value is square root of 34. But to graph it, I've got negative 5 plus 3i. So on my x-axis, I'm going to go to the left 5 spaces. 1, 2, 3, 4, 5. I'm right here. And then I'm going to go up my imaginary plane, 1, 2, 3. So over here, that point right there is the graph of negative 5 plus 3i. So I did both of those things, right? I got the absolute value and I graphed 5 plus 3i. All right, so that's that first one. So what if I have another one here and I want to get that absolute value, and then I also want to get the graph of it. All right, so if I have 6i and I want to graph 6i and get the absolute value of it, so really first off I just have 6i. So basically if I graph it on the imaginary axis, which is our vertical axis, right? 1, 2, 3, 4, 5, 6. All right, so here's the graph of 6i. That's it. Now, if I want to get the absolute value of 6i, I got absolute value of 6i equals 0 plus 6i, right? Equal 0 squared plus 6 squared equals square root of 36 equal 6. So there we go. Got the absolute value and I got the graph of a plus bi. So what we're doing here on the absolute value, so the absolute value of a complex number is its distance from the origin on the complex plane. So basically, here's what we're doing. The absolute value of a plus bi is going to be the square root of a squared plus b squared. I'm going to grab those values, a squared plus b squared. So that's why I got this, a squared plus b squared. All right, so what we did was we graphed on the complex number plane by simply keeping our x-axis and then transforming that y-axis into our imaginary axis. Now let's add and subtract some complex numbers. And we can write the sum or difference. So if I have 4 minus 3i, and I want to add negative 4 plus 3i, I'm going to basically treat the coefficients that have the imaginary numbers that have a coefficient in front of them, I'm going to keep them together. I'm going to treat them as they are the same, if you will, the same variable, like we used to work in variables. But I'm going to combine these two together just so we have our work. So we got 4 plus negative 4 plus negative 3i plus 3i. So basically I have 0 plus 0 equals 0. All right, so what I did was I used the commutative and the associative properties to sort of group those together, and we got them together. So let's simplify another one here. If we have 5 minus 3i minus negative 2 plus 4i, let's group those together. We've got 5 minus 3i first, minus, so if I've got negative and negative, so I'm going to make that a plus, and then negative and a positive minus 4i. Now I've got 5 plus 2 minus 3i minus 4i. I can combine these guys, so I've got 5 plus 2 is 7. Negative 3 plus negative 4i, that's negative 7i. So I've simplified that to 7 minus 7i. So I can work with those complex numbers in a very similar manner that I have done in the past, but they're a complex number, they're not a variable. So we can also multiply complex numbers using the same theory, right? 3i times negative 5 plus 2i. So already I know I can use the distributive property. I've got 3i, negative 5 plus 2i. 3i times negative 5, that's negative 15i. 3i times 2i, so that's going to give me 6i squared, right? All right, and then I'm going to substitute negative 1 for I squared, right? Remember that from our work? So I've got negative 15i plus 6 times negative 1. So that gets me negative 6 minus 15i when I substitute. All right? So very similar manner, if we have something that also looks familiar, we have 4 plus 3i, and then negative 1 minus 2i. So I can use the distributive property, or I can use FOIL, right? So first is 4 times negative 1, that's negative 4. And then I've got 4 times negative 2i, that's 8i, that's my outside. Inside is 3i times negative 1, so that's minus 3i. And then my final ones here are 3i times negative 2i, so that's minus 6i squared. You see that I squared, what are you going to do? You're going to substitute negative 1 in for it. So I'm going to just write that out. So we have negative 4 minus 8i minus 3i minus 6 times negative 1. All right, combine my like terms. I end up with 2 minus 11i. All right, so that's what I did there. I got my product, and I sort of used the something similar that we've been working with. All right, so let's look at what's called the complex conjugate. All right. Now, if we have a plus bi, we have a complex conjugate of it, and that's simply a minus bi. That's what it is. You got a complex number, its conjugate is a minus bi. So we can use complex conjugates to simplify quotients of these. Remember, in quotients, we kind of did the reciprocal. So let's look at using a complex conjugate to come up with a quotient. So if I have 9 plus 12i, or 3i, so I'm going to use, I'm going to multiply both sides by 3i, right? So I've got, I'm going to distribute here. That gives me 27i. I'm sorry, by negative 3i. So I've got negative 27i, and then minus 36i squared, and then all of it over negative 9i squared. All right, so you know what we're going to do is take that I squared on at the top and the bottom, and we're going to substitute in our negative 1. So I've got negative 27i minus 36 times negative 1. All of that over negative 9 times negative 1, right? Simplify that. We got 36 minus 27i, just putting them in order, over 9, okay? And I've got 36 divided by 9 equal 4, 27i divided by 9 equal 3, so minus 3i. All right, so I multiplied the numerator and the denominator by the complex conjugate of the denominator, and then I substituted negative 1 for I squared. So that's getting your quotient by using the complex conjugate. You can also factor using complex conjugates. So let's do some factoring here. So if I've got a factored form of 2x squared plus 32, just as a review of greatest common factor, right? Looking at the multiples and then factoring out. So I can factor out a 2. Remember that? That leaves me with x squared plus 16, right? So if I use, if I factor out the greatest common factor, then I can use a squared plus b squared. So I can kind of factor them out, x plus 4i, and then multiply that x minus 4i. So I'm getting the complex conjugate. So I end up with 2x plus 4i, that's the complex conjugate, times x minus 4i, right? Because x squared times 16, that gets me x plus 4x minus 4. So I get a 0 in the middle. So the complex conjugate of that looks like that. So I end up with 2x plus 4i and x minus 4i. And I can go back and check my work and factor those. So we can also use the quadratic formula to look for the imaginary solutions of some of these. So let's do that. Quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a. And just remember that that we're going to be, that those zeros are have either no solution, one solution, or two solutions, right, around the where it hits the x-axis, that parabola. So we're going to use the quadratic formula, and we're going to start out with this equation, 2x squared minus 3x plus 5, set it equal to 0, and then we're going to use the quadratic formula and fill in our, we've got an a value, b value, and a c value. All right, so I've got equal negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times 5. All of that over 2 times 2. All right? Let me simplify. So I've got negative 3. Well, that's a positive 3. Plus or minus the square root of, grab your calculator. So I end up with 9 minus 40. So 9 minus 40, see where we're going with this. And all of that over 4. All right, so I end up with 9 minus 4, so 3 plus or minus the square root of negative 31. All of that over 4. So then I've got 3/4 plus or minus the square root of 31 over 4i, right? So that square root of negative 31 is I. So I can then go and look and see what my solutions to this quadratic are. Where is it going to hit that x-axis? So if you go into Desmos, you can use that that x-axis, the y-axis, convert that to making that our imaginary number. Just kind of giving you a way to also look at it. So over here, I've created my imaginary axis, which used to be the y-axis, and then I've kept my real number axis, which is over here, which is my x-axis. And then we've got a couple of things here. So that blue point that I've created here, it's going to be the values that represents the complex number itself. So as you can see, that's where it's going on the axis. And it can go that way or that way. It's going to represent that a plus bi on the scale. So you can play around with it also in Desmos, or you can just simply understand the plotting of it. We're not going to graph in Desmos like you would have, like you do with our regular quadratics. All right, so that's complex numbers. Now it's your turn.